Hello, Matt G for IYT here, and today we're looking at the full license mock exam number 1, version 1.6, and we've reached question 19, which reads: the modulation index of an RF signal is the ratio of A, the maximum frequency deviation to the nominal unmodulated carrier frequency, B, the amplitude of the unmodulated carrier to the variation in amplitude of the envelope, C, the frequency deviation from the nominal carrier frequency to the frequency of the audio signal, or D, the instantaneous frequency deviation from the nominal carrier frequency to the maximum deviation. So let's start by reviewing the modulation index. And if we flip over to the full license manual, we've got this section here on amplitude modulation. And of course, with AM, we are modulating our carrier with an audio signal, and the modulated carrier will vary in amplitude, and it is these variations in amplitude, or the envelope of that modulated carrier, which represents the information that we wish to transmit. And so the amount by which this carrier changes is potentially a property that we would be interested in. And it also explains this idea of the depth of modulation, which is a ratio of the amplitude of the unmodulated carrier to the amount by which that changes with an audio signal that's used to modulate it. So we've got the amplitude of our carrier that's unmodulated, and then we will modulate that carrier, we will change its amplitude with an audio signal to produce this envelope, and we get this amount by which it changes. And if we divide B by A, we get this depth of modulation. So the depth of modulation is a property we're interested in with AM. If we have a low depth of modulation, which basically means our carrier isn't modulated a great deal by our signal, then we would find that we had quieter audio in the receiver. If we had a very high depth of modulation, that would lead to distortion and potentially interference with neighbouring frequencies. Generally not something we'd want to do. So in AM we have this idea of depth of modulation. Now if we come down to, there's a similar section about frequency modulation, and of course with frequency modulation our audio signal is modulating the frequency of the carrier. So we can see here as the audio signal peaks up, our frequency is peaking here, is getting higher, and then as the audio signal comes down in amplitude, then our frequency is getting lower. And so overall there is going to be we're going to have a carrier which is then going to deviate one way or another as the amplitude of the audio signal changes. Now, unlike the depth of modulation, there really isn't really a limit to the amount of deviation that you can have. You could have signals on the amateur band. You might have signals that have a 5 kHz or a 2.5 kHz peak deviation, so the maximum amount that they deviate for the carrier. Whereas if you go to sort of VHF FM broadcast, so you like your Radio 1 or your Radio 4, that kind of thing, that could deviate by a peak deviation in either direction as much as 75 kHz in either way. However, the amount of deviation is going to determine the overall bandwidth that is required to transmit that signal, and actually this section does go into that and shows how the overall bandwidth is the maximum audio frequency plus the peak deviation multiplied by 2. So while the bandwidth is a good way of understanding the amount of spectrum that is required to transmit a signal, if we can take these two values and express them as a ratio, it allows us to more directly compare two transmitted signals which could have wildly different peak deviations or maximum audio frequencies, and that's how we end up with the modulation index, which is the peak deviation divided by the maximum audio frequency. And in a way it's telling us the range of deviation that is required to encode the maximum, the bandwidth of audio frequencies that we want to transmit. So a common way that we use the modulation index to compare signals is when we're talking about a narrow or a wide signal. So when setting up a receiver, perhaps you may have seen that it can be in narrow FM or wide FM, and that's typically related to the modulation index, which would take on the symbol B, or B with a tail for beta, and when B is less than 1, that is typically a narrow band FM or NB-FM signal, and when it is greater than 1, we usually call that wideband signal. So the modulation index is the ratio of the peak deviation to the maximum audio frequency. So let's now come back and look at our answers. So we've got answer A, the maximum frequency deviation to the nominal unmodulated carrier frequency. Well, that's not quite right, because it's not the carrier frequency that we're looking at, but it's the audio and the maximum audio frequency. So we're going to strike that one off. B, the amplitude of the unmodulated carrier to the variation amplitude of the envelope. Well, that does sound a little bit like what we need. However, when we're talking about AM, and especially within the confines of the full syllabus, when we're talking about AM, it's depth of modulation. When we're talking about FM, it's modulation index. Now, modulation index is a term that can be used more generally to describe, for instance, properties of phase modulation as well. But within the full syllabus, we're talking about FM, so we can strike that out because we're talking about FM here. C, the frequency deviation from the nominal carrier frequency to the frequency of the audio signal. And we've also got D here, which is very similar, the instantaneous frequency deviation from the nominal carrier frequency to the maximum deviation. And the key word here is instantaneous, which would mean that we would be constantly evaluating this as the signal was changing. So instantaneous is not right. We typically talk about the overall, the maximum frequency deviation, not the instantaneous frequency deviation, so we'll scratch that one out. Instead, we're talking about the frequency deviation from the nominal carrier frequency to the frequency of the audio signal. Let's cross-check that again. Peak deviation over max audio frequency. We're going to go with option C here. Let's skip down to the answers, see if we got that right. And of course, we see for question 19, we've got option C. Thank you very much. I'll catch you for the next one.